Hello, everyone. Thank you so much for coming here. I know you're probably really tired, exhausted, and want to get out of here, so I really appreciate that you made the effort to come to this. And thank you for the organizers for inviting me. It's been an amazing event so far. I'm going to be talking about the big data universe. But first, I want to thank my two colleagues down there, Bruno Merin and Beatrice Martinez, who helped me a little bit with the slides. So to start off, I want to talk about this image here. Let's see a raise of hands of who in this room recognizes this. Great, most of you. For those of you who don't know what this is the first ever image of a supermassive black hole, one of the densest things that we know of in the universe. It weighs 24 billion times the mass of our sun. The light in that circle you see is the last photon orbit. It is the last orbit of light before it falls into the event horizon where light can no longer escape. This is one of the coolest things in astronomy right now. Cool, one black hole. This black hole lives in this galaxy, M87. And you can see the black hole is minuscule compared to the galaxy it lives in. It's 10 million times smaller. And to put this galaxy into perspective, the galaxy it lives in is 5 times smaller than the moon. And the moon is, if you stick your hand out and your thumb up, the moon is typically about the width of your thumb. So this black hole is really tiny. So how do you observe something so small? Well, you have to combine 8 radio telescopes from around the world. These points represent the positions of the radio telescopes, which together make the Event Horizon Telescope. And they simultaneously pointed at this supermassive black hole to observe it, all the while talking to each other. Collectively, they made a telescope that was essentially the size of the Earth. That is how you observe something so small. The image was created by observing the black hole over the course of a week, and in total, they gathered 5 petabytes of data. That's 5,000 terabytes of data. It took hundreds of hard drives, just like this, to store it all. It is a lot of data. To put it into context, this is how much data the New York Stock Exchange produces. So it's the same data that the New York Stock Exchange produces over about 13 years, and the same amount of data that Twitter produces over the course of 2 years. It is so much data that for an average person's internet, which has an upload speed of about 30 megabits per second and a download speed of about 60 megabits per second, if you do the calculations of this, it would take you about 44 years just to upload it all to the internet, and then another 22 years to download it all. So that's a long time. I work at ESA, the European Space Agency, and we have some of the fastest internet in the world. Our download speed is about 20 times that of the average person. But even with a big company like the European Space Agency, it would still take us 4 years to upload all that data and another 2 years to download it all. Yeah. So thankfully, the Event Horizon Telescope people did not do that. They packed all the hard drives into boxes and crates and flew it by airplane to the destination, to MIT and to the Max Planck Institute, where they analyzed the data. Actually, even this took a little bit more time than they expected because one of the radio telescopes was in the South Pole. So the data from the South Pole was not able to be collected most of the months of the year where winter over happens and airplanes can't get in and out. So that was like the last kind of piece of the jigsaw to get sent to the data analysis centers. Cool. So to process this data, it took 2 years of time. 2 years applying different methods to get an image like this one. And thankfully, both of the methods that they tried gave consistent results. They both looked like the black hole. Because it would be quite worrying if after 2 years you ran your code and you realized, oh no, they gave different answers, then what would you do? So thankfully, they agreed. I work with space data. So this is a little bit different from Earth-based data. And in the next bit, you'll find out why. This is the European Space Agency Centre's Science Data Center. This is where we archive all of our space data. This is one of the computer farms. I don't know why I'm taking notes in there. That's not what normal people do. But here is where we store all of the data from all of our space astronomy missions. We store data from across the solar system, right close by to the sun, all the way out to Saturn. We have data going back to 1990. These are things like flyby missions, these are landers, these are sample return missions, and rovers. So all of this data comes in different formats too, and we need to collate it all together. But it's not the only place that we look. We look beyond the solar system, across the entire electromagnetic spectrum, from down to microwaves and radio waves, all the way to the very energetic X-rays and gamma rays. The extragalactic missions, like these ones here, these date back to the 1970s. So that's a lot of data to accumulate and store and collect together, even though they're all different formats. All the ones below this line are existing missions, right? And all the data that we have at the ESA archives right now only accumulates to 2 petabytes of data. So you might think it's quite small. It's smaller than the black hole image that we saw that was really, really small. I'm going to talk mostly about this mission up here, Euclid. This is the mission that I work on at ESA. Euclid is a space-based telescope, and it's going to be launching in 2022 and run over a course of 6 years. Over the course of 6 years, what it wants to do is measure the dark universe. So figure out what is dark matter, the sort of glue that holds all of our galaxies together, and try to understand what is dark energy, what is making our universe expand. But dark matter and dark energy are called dark for a reason. It's called dark because we don't understand what they are. We've never found any of the particles that could contribute to it. So how can you see dark energy if we don't know much about it at all? The answer is to look at the structure of the universe. Here we have 2 different simulations. They're dark matter simulations. And you have 2 input cosmologies. That means 2 different physics. On this side, you have a lot of dark energy. And on that side, you have mostly dark matter. And you can see that over time, the dark matter particles, they cluster together. And this is due to gravity. The dark matter particles have mass, so they gravitate towards each other. And the more dark matter you have, the more they cluster together. And the more dark energy you have in the universe, the more voids the empty areas expand. So you can see on this one, you've got very large voids, and on this one, you have very dense clusters. So by looking at the distribution of dark matter in the universe, we can figure out how much dark energy there is in the universe. Cool. But we also can't see dark matter. Dark matter doesn't interact with anything, and it doesn't emit any light. So how can we figure out where it is? Well, we can actually see dark matter through an effect called gravitational lensing. So in gravitational lensing, imagine if you have a faraway galaxy. The light emitted by the galaxy is perturbed by the gravitational influence of some mass. It could be a big blob of dark matter, or it could be a giant galaxy cluster. So imagine you have like a torch. We're taught in school that light should travel in a straight line, right? But if gravity of Earth is strong enough, Einstein predicted that the light would actually be bent to the ground, pulled by the Earth's gravity, just like we are pulled to the Earth. And this is exactly what gravitational lensing is. What it actually looks like in practice is this. If you've got a background of perfectly circular galaxies on the sky, and you were to put a big blob of dark matter in between us and those galaxies, you would see that the galaxies distort their shapes perpendicular to where the dark matter blob lives. And the more mass there is, the more distorted they are. Okay? So, simple. We measure the shapes of galaxies, and then we can determine where the dark matter is in the universe, and then we can use that to figure out how much dark energy there is in the universe. But it turns out that it's not actually that simple. Why? Well, firstly, galaxies are not perfectly circular. They're elliptical in size, and they come in all different orientations. Secondly, this gravitational lensing effect that we call gravitational shear changes the shape of a galaxy by the order of 1%, so it's tiny. On top of that, if you were observing them from Earth, you would get some blur from the atmosphere. Even observing it from space, we get some blur from the telescopes. On top of that, we have cameras that actually detect the galaxies, and this pixelizes our images. And on top of that, we have a lot of noise. The noise is typically like 10 to 30% higher than the gravitational shear signal that we're looking at. Fine. Euclid's solution is to observe as many galaxies as possible so that we can get a statistical average over many, many galaxy shapes. Euclid will observe 2 billion galaxies in total. This is an image of the entire sky as taken by ESA's Gaia mission. Along the center here, you have the disk of our Milky Way galaxy. And then down there, you've got the large and the small Magellanic Clouds. Okay? Euclid's main survey, the wide survey, will observe all of those regions shaded in green. So it misses that central strip, the galactic plane, because you get zodiacal light from dust, and it misses the ecliptic plane. It observes 15,000 square degrees. That's about a third of the sky. But this is much more than all of the existing weak lensing surveys to date, which typically observe about 200 square degrees at a time. Up there, that tiny dot is the moon for comparison. So if you think back to that tiny pixel that was the black hole, we are observing so much bigger volume and area than that black hole. Okay. Cool. So in order to make sure that what we're doing is really correct, because we only have a 1% signal, we need to validate everything with simulations. So Euclid has the largest simulation built to date. It's an end-to-end simulation. So you put in physics that determine what the universe looks like, and it propagates through time, through our telescope as we observe it, to get the simulations as we would receive at the end of this mission. It consists of 2 trillion dark matter particles. So it's a pretty huge simulation. And they ran it here. This is the Swiss National Computing Center. It's a Pisdane supercomputer. It's the 6th fastest supercomputer in the world. And to run our simulations, it took 80 hours on 5,000 of their GPU nodes. It cost 270,000 euros to run this simulation. So there is no room for errors. You can run this once or you're going bankrupt. We run this once every year with new cosmologies. Cool. This is what the simulation should look like. It's a dark matter simulation. But you can see that we only simulate 5,000 square degree of the universe. This is a third of what Euclid will actually observe. And the output of the simulation data will be about 400 terabytes of data. So it's still quite a lot, but not quite as much as our black hole. But it's still too much for any scientist to download and analyze. So we need to compress it down to catalogs. We compress it down to point estimates of shapes of galaxies and their positions on the sky. This is the Rockstar catalog, and it's still 5.5 terabytes of data. And we compress it down to dark matter count maps. And this is still 1 terabyte of data. So it's still quite a lot of data this simulation produces, and scientists need to analyze. But the special thing about space data is that we don't have wires connected to our telescopes to receive the data. The Euclid mission lives at a location called the Lagrangian point 2. It's 1.5 million kilometers away from the Earth. It's a very stable point in our solar system, and it's also very low radiation. And this is really important because we're trying to measure the shapes of galaxies to 1% accuracy. You can't have any wobbles. And even like too much sunlight will affect us being able to measure these shapes. So every single megabyte of data that we send back to Earth is super precious. We need to have deep space antenna to collect this data. And ESA have 3 of these antennae. DSA-1 is in New Norcia in Australia. DSA-2 is in Cebreros in Spain, just north of Madrid. And DSA-3 is in Malaga in Argentina. And they're all controlled at the Mission Control Center in Darmstadt in Germany. This is one of such antenna. It's the Cebreros one in Spain. And you can see like little humans down there for size comparison. Every day, this radio antenna can only communicate to our spacecraft 4 hours a day, right? And this is even though we have a steerable antenna on our space telescope, which maximizes the amount that we can communicate to Earth. Because most space telescopes have a fixed antenna, you can literally only communicate to it when it's directly overhead. Every day, we download 850 gigabit of data. That's 100 gigabytes of data every day. And it is crucial that we can do this, because on board of Euclid, there is only enough storage to store 3 days' worth of data. So if we leave it longer than 3 days, all that data that we've collected will start to overwrite itself, and that would be awful. So we need to plan it really well. After collecting the data at those space antennae, they get sent to the Science Data Center, which is where I work in Madrid. This used to be a telemetry center where they did tracking and the commanding of telescopes too, but that's moved all to Germany now. Right now, what we do is a quick look analysis. So we get the data, we do a quick look of it to check that the data looks like how it should be, and there's no problems with any of the settings. We archive the data, and then we distribute it to scientists around the world so they can do science on it. Okay? This is an aerial view of the site. So this is where we store the data in this building here. You can see it's a lovely site. We have a wonderful castle. We have tennis and football pitches. This is the largest astronomical archive center in the world. Because NASA, they store all of their data separated across different locations. But ESA, we store all of our science data center, all of our science in this building. And guess what? Guess where the backup data is stored? The backup data is stored in this building. There is nowhere else on the Earth that our data is stored. Actually, we're slowly transitioning to store it in Esrin in Italy, but at the moment, all of the data is here. Because it turns out it's quite a lot of effort to transport that much data to another site. But so far, everything is of very low risk, because our data archives are backed up by 3 generators, and they are working on diesel, so they could keep going forever. They are stored in vacuum chambers, so if the entire site were to burn down, our data archives will still be standing. And anyone who works in the data archives, we have to have special training to make sure we don't get locked in there and suffocate. The biggest risk to our data archives is if a plane or a helicopter crashes into any of our buildings. That would be disastrous. But that has a very low risk, because ESA is a completely separate country from Spain. We have our own laws. We don't follow Spanish laws. You need a passport to get in and out. And we have our own airspace. So planes and helicopters, they cannot fly through this area. And actually, what was quite funny was that last year, we had a fire up by this castle. And so obviously, helicopters were flying overhead, bringing water to try and put this fire out. And everyone at ESA were like, what are they doing? They're not allowed in our airspace. Yeah. At ESA, our priority at the moment is to make our data as attractive as possible. Because we're no longer living in an era where scientists are fighting over data. We're quickly moving into an era where the data will be fighting over us to analyze them. And to do this, we need to make our data very visually attractive and very easy to access. And these are the biggest challenges for the data archives at the moment. So to do this, we've been building a platform called ESA Sky. So it's based on a hierarchical tiling image architecture called HIPS. And this enables you to zoom in and zoom out of large amounts of data very, very quickly. You can quickly visualize like terabytes of data, but only bring up kilobytes of data. And that's allowed us to do very quick rendering on web pages. Okay? This is what it looks like in practice. This is a real site. You can go and access that, sky.esa.int. And anyone can just go there. You don't need to log in or sign up or anything. And it looks like this, like the hierarchical tiling system. You can see how quickly you can zoom out of large amounts of imagery and zoom in to large amounts of imagery very, very quickly. We have wavelengths covering the entire electromagnetic spectrum. So gamma rays, soft X-rays, and radio down to submillimeter wavelengths. We have the data from not only space-based missions from ESA, we have space-based missions from NASA too, and also ground-based telescope data is on there to access too. And you can also change around the color schemes if you're not happy with them as well. This is where it will be very easy for people to access data. Here shows different surveys of many of our telescopes and all of the telescopes on there. You can just click on a survey, and it will tell you which area is covered, and you can click on the links to bring you directly to ESA's archives and download the data so that you can work on it. So it's very, very easy. Okay? One of my favorite parts of ESA Sky at the moment is this icon up here, this hat. This scholar icon, when you click on it, it points you to every single academic paper available on the web of the different sources. So you could scan through ESA Sky and find something interesting. You could click on that hat, and you could see, oh, wait, there's no paper on this object. That's a paper waiting for you to write. OK. To make it easier to use, ESA are also developing a code-to-data platform. They're calling it the Science Exploration Platform. And the idea is that we don't want users to be downloading like petabytes of data and analyzing it themselves. There's no way they can do that. They don't have the storage for that. So we want people to upload their code to where the data is stored at ESAC, and then run it on like Jupyter notebooks connected to Spark clusters. And also, there's a lot of push to use like cloud computing, because one of our department heads just came from ESO, and he turned ESO around by converting them to cloud computing. But with all of this platform in place, we still have the problem of analyzing the data. This is what one piece of Euclid will see. It's a simulation, obviously, because Euclid won't launch till 2022. But you can see that it's really, really nasty. What we're interested in are things like these. These are galaxies. And there's 2 billion of these hiding in this data. But we have to sort it out from, for example, the stars. There's ghosts, which are kind of like effects from stars, imprints. We've got cosmic rays, which are very highly energetic particles that saturate our pixels. And these bleed as we read them out of our image. And we've also got asteroids. There's a lot of things going on. So to analyze the data, to get those 1% reading, 1% measurements of their shapes, we first have to sort through all of this mess. And it's actually ESA's role to do this. We have to prepare our data science-ready for the scientists. We can't give them data like this. They wouldn't know what to do with it. Even though Euclid will be producing 10 petabytes of raw space data, after the science cleaning for it, when it's science-ready, it will be over 30 petabytes of data. So it's too much data for us to analyze with traditional methods. And that's why scientists like me are turning to machine learning. We need fast methods to analyze huge amounts of data. But we're scientists, so many of the methods that we've been applying are still relatively relatively beginner kind of machine learning methods. These are things like, for classification and detection, things like k-means, where you will try to find the centroids of clusterings of objects that are similar to each other. And for example, this was demonstrated by Romani et al. In 2018, where they characterized the signatures of light emitted from galaxies. Things like dbScan, where you're looking for clusters of objects which have a minimum number of objects that are similar to it in its region. This was demonstrated by one of my colleagues, Hector Canovas, to figure out which stars were connected to a star-forming region. K-nearest neighbors, classifying objects as the class of objects which are the most of the neighbors that are surrounding it. This was used by Michelle Lochner in 2016 to define types of supernovae. So these are exploding stars at the end of their life cycles. Okay? And also the decision tree, where you've got nodes, and it splits off depending on the conditions that you set. And this was used by, for example, Barron et al. In 2016 to find weird galaxies. Cool. These methods are relatively, they're good, but if we want to work on the raw data to analyze it as it comes down, we need to focus on, for example, convolutional neural networks. This is where you're scanning across the images and slowly reducing the dimensionality of them to classify them as the classes of objects that you are doing. So I showed that in my paper this year to classify asteroids, but also galaxies and stars and cosmic rays, with my highest architecture getting 97% accuracy. And also Schaefer did this in 17 to look for strong lensing around galaxies. So this is where the gravitational lensing is so strong that it produces arcs or rings on the sky. Okay. But when you don't have a lot of data, you can use things like transfer learning. So this is a convolutional neural network called Inception. And it's really big. It's got millions of parameters, and you can use things. You can train it on a huge data set like ImageNet, which contains millions of images with thousands of different classes not related to anything astronomy. But once you've trained the weights and the biases of this model, you can fix the initial layers and just retrain the final layers for your astronomical data set. So retrain it to learn the classes of asteroids, of galaxies, of stars. And this works extremely well, and it reduces the amount of data you need to train the convolutional neural network. But for convolutional neural networks, you also need labels. And that we don't have a lot of either. Usually, you have a scientist sitting there looking through thousands of images of data. This is very ineffective. It's slow. It's unreproducible. So one of the methods we've been turning to is the use of citizen science. So citizen science is when you outsource those kind of mundane tasks, such as classifying galaxies, etc., to the general public. And we have a very successful platform for doing this. This is called Zooniverse, and it contains hundreds of different projects, not just astronomy-based, although that's where it started. You can go on there and classify, I don't know, penguins and giraffes and elephants. So far, there's like 2 million volunteers and hundreds of millions of classifications of all different kinds. To show you an example of the kind of stuff that they've been doing, they've been classifying the morphologies of galaxies. Each one of these letters are actual galaxies. So there are so many weird galaxies out there that you can have multiple letters of every single letter in the alphabet. That says Hello, Jay on the Beach 2019, by the way. We can use it to classify star-forming bubbles. This was done by one of my collaborators, Sarah Kendrew. And at the center of this bubble is a very energetic star. And it ionizes the gas and dust around it, pushing it out, and then shocking the gas to produce this dust bubble. It would take scientists years to analyze the same amount of data that these citizens do in weeks or months. So then that allows scientists like Sarah to focus on the real science. And from the data of this, she was able to figure out that this shocked region produces triggered star formation. So the star at the center produced so much energy that it was able to trigger more stars to form around this bubble. And you can also use it for gravitational waves. So gravitational waves are ripples in space and time that you get when two massive objects, for example, two black holes, merge together. And the detectors of these kind of signatures are so sensitive that not only could it feel an earthquake happening on the other side of the world, but it would be able to detect a bird flying above the detector. That's how sensitive it is. But there's also a lot of glitches in these experiments, and so citizen science has helped a lot to discover new types of glitches. Cool. After classification and detection, another important thing is to compress the data and compress the model. Using things like neural networks and emulators, for example, principal component analysis to reduce the dimensionality of your data by looking at the eigenvectors, the largest variances in each of your axes of your data. You can use emulators, such as mixture density networks and neural network emulators as well, to compress models down in size. So for example, those simulations that I talked about earlier, those with trillions of particles costing 270,000 euros to run each time, you could train a neural network to simulate that, and it would be run so much quicker and so much cheaper if you were able to simulate some examples for the machine learning to train on. But there's still a lot of methods that scientists have not been really open to at the moment. This is some data from Gaia. This is 2 million stars in our galaxy. And these motions are real. Gaia looks like this. This is a 2-scale model that we have at ESAC, and that's me for size. Gaia does not download the images of each star in the sky. Instead, it uses edge computing to compress the data into positions and velocities of the stars on the sky. And that saves us so much in terms of download bandwidth. And it's also used in Mars rovers, because on Mars, the data takes like 6 to 20 minutes to communicate back and forth with a rover. And you can imagine there could be dangerous situations where a Mars rover is driving and it suddenly falls off a cliff. We wouldn't be able to tell the rover to stop. And that would be like billions of euros lost there and then. We need onboard computing to help them make right decisions as it goes. Upcoming methods like continuous learning with GANs I don't know if any of you, most of you might be familiar with GANs. So you have like two neural networks competing with each other. One generator trying to generate very realistic data and a discriminator trying to tell it apart. GANs were able to produce images like these. These are not real people. These are completely machine learning generated. But what if on Euclid, instead of collecting our data, we decided to put a GAN on there to learn the distribution of the galaxy shapes that we were seeing, and instead of downloading all of that data, all of the images that we were seeing, we would just have to download the GAN, the trained generative adversarial network. I suggested this to my boss, and he was like, I don't think scientists would be very pleased if you spent over $1 billion on a space mission and all you gave was a neural network return. And one thing I'm really excited about is federated learning. Because even bringing code to the data, us as data providers, ESA, we will have to have huge computing facilities, loads of processors and stuff. But imagine if at ESA we had the data, sure, but we also had a supermodel. Not that kind of model, but a machine learning model, for example. This supermodel could be replicated by people around the world, and they could train that same model on fractions of the data. And after they trained it on the fractions of the data, they could send the trained network back to ESAC, where the model would be updated according to like the majority of the crowd. So if people's models said favored more of this weight, then it would favor more of that weight in the final model. So that's something I'm quite excited about. So I guess I hope I've convinced you that space-based data is very precious, because every megabyte we have to build a spacecraft to go up there. It costs billions of euros. We have to download it, which takes a lot of time and effort, and we have to make huge simulations just to verify that this would work. But 10 petabytes of data is really nothing, right? On Earth, we can afford to get much larger, because our telescopes are all connected to each other. This is LSST, a telescope being built in Chile at the moment. Okay? And it is going to be finished very soon. Its first flight will be 2022, and it will operate over 10 years duration. Every day, it's going to be downloading, well, it's going to be generating 15 terabytes of data. That's a lot of data. It's looking for things like this. These are transient objects. So this is like a different day as time goes by. You can see this object in the ring disappears, or appears and then disappears, right? These are transients. These are things like supernovae, like the death of stars. They're things like asteroids, comets, and gamma ray bursts. It's also being used for gravitational lensing. For all this stuff to happen, LSST has to scan the entire sky every 3 nights. And it's going to do this for 10 years. It's going to produce about 60 petabytes of data. That's a lot of data. But can it get any worse? And the answer is yes. This is the Square Kilometer Array, SKA. Okay. And it's a collection of radio telescopes and radio antenna being built across South Africa and Australia. We've got a little time before this launches, 2030, but it's going to be generating 2 terabytes of data per second. That's 62 exabytes of data per year. That's like 62 million terabytes of data per year. That's a lot of data. It's going to be generating 10 times more volume than the entire internet generates per year. It's incredible. Those little antennae on there, these are life-scale models of them. You can see they're pretty huge. And these are the locations that they're going to be built in. So you've got the Murchison Radio Observatory in Australia, in Geraldton, and mostly in South Africa down there, but also spread out across Africa, in Kenya, Botswana, all over the place. And there's going to be thousands of these radio antenna and radio telescopes. They all have to talk to each other. That's the difficult part. Anyone who's been to Australia knows how slow the internet is in Australia. 7 megabits per second. It's so slow that people working on this project are having to put in fibers, especially for this telescope. Okay? It's a lot of data. And do we really need all this data? The answer is yes. This is Galaxy Centaurus A. It's what it looks like in the optical. We're looking at it kind of on an edge. This is the disk of the galaxy. This is what the radio would see. It looks completely different, right? You can see active galactic nuclei, so the supermassive black hole, and the jets that it's emitting. This is seen by the Very Large Array. So unless we get composites of multi-wavelength data, we would not get the full picture of what this galaxy actually looks like. We need as much data as we can get. But that data looks really scary. Event Horizon Telescope is giving us 5 petabytes of data. Euclid, 10 petabytes of data. LSST, 60 petabytes of data. SKA, 200 million petabytes of data. You know what their current plan is to deal with this data? They're going to throw away 98% of it at random. And still, then there is no way that we can deal with it because current technology just does not allow for it. We don't know how to store it. We don't know how to transport it. We don't know how to analyze it. If you just write on your CV that you can help SKA, literally any academic institute will hire you. They have a lot of funding. So I just want to end saying that we have huge challenges in astronomy in this upcoming big data era. We have a lot of data coming. We need to know how to collect it, both from Earth and from space, transport it, deliver it, building platforms to visualize it and analyze it. So we need developers like all of you guys here, not just scientists like me, because we have no idea what we're doing. So let's collaborate, and I will finish there. Thank you so much for your attention, and I'll take some questions if you have any.
Right. Thank you so much, Maggie. So we do have a few questions here for you. I'm going to start off with the first one here. So it's, how do you prepare the software to analyze the data for black holes or Euclid data if you don't know yet the data that you'll obtain and the quality of volume?
We do know what the data will look like because we build the instruments, and we have to build the simulations. No one would give you like €1 billion to build a space telescope if you can't demonstrate to them that you can actually analyze the data.
OK, fair enough. And here's another one. It's, how do you have a quick look at such a big volume of data?
So we don't look at every single image. Mm-hmm. We have screens. At the moment at ESEC, we have the XMemorium, and that downloads images in a stream. At Euclid, the CCD that we're sending up, the camera that we're sending up on Euclid, is the biggest we've ever sent to space. So the image is actually huge. Kind of image that I showed you with the simulation, that was half of a CCD. and there's going to be 36 of them, like at every image that you take. So you can imagine that the image that it takes is going to be huge. So yeah, we can't look at all of it. We'll look at fractions of it at a time.
Okay. All right, and we have one last question here from the doc that we created. It says, how do you send such a big data volume produced by the missions back to Earth? And what bandwidth do you need for that?
That was actually on my slide.
Yep.
K-band and X-band. I am not a kind of expert on that stuff, but I will provide the slides to you guys, available on the net, so you can look through them again if you're interested.
Yeah, and you can tweet it out to us, and then we can retweet you.
Yeah,
all
that
right.
would be great. Thank you.
Can we give a big round of applause to Dr. Maggie Lieu?
Thank you.